Okay, so earlier we have analyzed some mechanisms and we have seen that each reaction mechanism can give rise to a variety of patterns in the complex plane plot of the impedance spectrum. Okay. Now, I want to show you some examples from literature, okay, where people have seen certain patterns in experimental conditions and many times they have analyzed it, and using RMA, using reaction mechanism analysis, they have been able to model this spectrum. Okay. This is not an exhaustive list. Obviously, there are many other publications with probably different patterns, but this gives you an idea of what are all possible. This is one of the simpler ones. Of course, people have seen data with just a semicircle or part of a semicircle. Here, this is an example with two capacitive loops. In all these plots, I am going to show you minus imaginary on the y axis and real on the x axis. Okay. High frequency, this is the starting point, high frequency data, and as you go to lower and lower frequencies, it forms one capacitive loop followed by a second capacitive loop. This can arise from many systems, but in this example, this has been seen for copper dissolving in a solution containing ammonium and hydrogen peroxide, and this has been analyzed using mechanistic analysis. You can see that the loops that I have drawn here are more or less equal sized, whereas the loops that are drawn here are obviously not of equal size. This is just to show that these patterns are possible. Okay. This is taken at one particular DC bias of 200 millivolts. Now, three capacitive loops, again starting at high frequency data starting near R solution, and then forming one capacitive loop, second capacitive loop and third capacitive loop. Here of course, I have drawn them very nicely or neatly. It may not form very clearly distinguishable capacitive loops, some of them may overlap to some level, but if you do electrical circuit fitting or equivalent electrical circuit fitting, you would know that two capacitive loop model will not be able to model this well. You will need a circuit with 3 time constants. Okay. One example of this is titanium dissolving in HF. This shows the first loop coming out nicely. Second and third loops are not that well separated, but you can also see that it cannot be modeled with only one capacitive loop from the mid frequency to the low frequency data. These are taken at two bias conditions, and at both conditions it shows 3 loops for both conditions, and this is in the region called active dissolution region. Okay. This is in 2015, and this is also analyzed using mechanistic analysis. There are many publications which show that inductive loops at low frequency can form. Okay. Of course, there are many more results with capacitive loops, but there are many publications or sufficient number of publications with inductive loops. This example is given publication by Professor Bourgeonneau, and this is molybdenum dissolution in acidic sulfate media. In this, they have modeled it using a film with a reaction. Okay. So, naturally here this is going from high frequency to mid frequency to low frequency. This is not a clean loop, but overall you can visualize and say this is a system where high frequency you have capacitive loop, high and mid frequency you have capacitive loop, and at low frequencies you have inductive loop. It is possible to have more than one inductive loop. Okay. So, this here starts at high frequency, goes to middle frequency, it forms one inductive loop, and then subsequently it has another inductive loop. And this is published in 1977, that means nearly 4 decades ago. This is iron dissolving in sulfuric acid, and this has been analyzed using mechanistic analysis. I do not remember the bias used for this, and I do not remember whether it is measured in pseudo galvanostatic mode or pseudo potentiostatic mode. In any case, high frequency to mid frequency it is capacitive loop, and then middle to low and very low frequencies it forms 2 inductive loops, obviously of different sizes, but you can also clearly see there are 2 well separated inductive loops at the low frequencies. Okay. You can also understand that 4 decades ago the computation power available for someone to model this is lot less than what it is now. The availability of software with optimization algorithm is also not going to be as good as it is now. So, if somebody has done this 4 decades ago, you can imagine how much challenge they have faced and overcome. Next example is data with 3 inductive loops at the low frequencies. Okay. This is in case of iron dissolving in sulfuric acid. This is published by Professor Kedam in 1981. This is the actual data. I have taken this or adapted this from the publication, showing 1, 2 and 3 capacitive loops at the low frequencies. I am sorry, 1, 2 and 3 inductive loops at the low frequencies, and these are actually with biases, and sometimes I will show you some examples with inductive loop, another example with negative resistance, another example with capacitive loops. It might be coming from one publication, okay, and this might be acquired in different conditions such as different DC biases. It might be acquired with different solutions. Okay. If it is in one solution, one electrode in one solution with different DC biases, all of them have been modeled using one set of kinetic parameters. So, I might show you 1 or 2 examples here, but they probably have modeled many of them simultaneously, because the aim here is to show you some examples of different patterns. I am not collecting all of them and showing here. So, in all these examples, I do not mean to imply that they have modeled this one spectrum with one set of kinetic parameters. Okay. Now, another example where you have high frequency capacitive loop, you have mid frequency capacitive loop and low frequency inductive loop. This is seen for copper dissolving in a solution containing glycine and hydrogen peroxide, and we have published this in 2010. This is for different DC biases. You can see for all of them you have a high frequency capacitive, mid frequency capacitive, low frequency inductive. It has not completed the loop, probably because the low frequency data was noisy and it was taken out or not shown here. And when we change the DC biases, the size of these loops shrink, the pattern remains the same, and this has also been analyzed using mechanistic analysis. Now, a little more sophisticated pattern. It is an extension of what we have seen before: capacitive, capacitive, inductive, followed by a capacitive loop. A capacitive loop here, the data is little noisy here, another clean capacitive loop, inductive loop and a capacitive loop. The numbers here represent the frequencies at which these data points have been taken, and this is published in 1986. This is a iron chromium alloy dissolving in sulfuric acid, again analyzed with mechanistic analysis. Now, inductive loop at low frequencies is the example we have seen before. It is possible to see inductive loops at mid frequencies. Okay. So, capacitive loop followed by an inductive loop followed by a capacitive loop again. This is an example where you have a capacitive loop. It is drawn in 3D plot here. So, complex plane plot is shown on the red color, and the blue color lines are actually form of Bode plots, where you plot imaginary value of impedance versus frequency, real value of impedance versus frequency with the frequency in log scale. This is modeled using electrical circuits in this particular case for Ti dissolving in HF at high DC potential, meaning a large anodic potential where transpassive dissolution occurs. So, initially in this case active dissolution occurs, that means the surface is not covered by protective oxide. Then current decreases with potential, when current decreases with an increase in potential. Okay. That happens in what is called passive region, but once the surface is completely covered with the passivating oxide, if we give very large positive potential, still dissolution can occur, and that is called transpassive dissolution. That was not analyzed in detail, but it was just modeled using electrical circuit. Another example is nickel deposition. Okay. This is published in 1981 by the group of Professor Appelboyen, and this shows clearly capacitive loop followed by an inductive loop at the mid frequencies and a low frequency capacitive loop, and this was modeled using mechanistic analysis. You can see the notation is little different. Now, some of us use Z imaginary, Z real, somebody else might use a slightly different notation to indicate R in ohms, G in ohms, minus Jg to indicate it is R minus Jg. R is the real part which normally we would write as Z real, Z subscript real, and G is what we would normally write as Z subscript imaginary. They have written it as minus Jg to indicate J is the imaginary number. So, when you, especially when you see some of the older publications, you have to just look at it carefully and understand what they have given here. A further extension of this, you have a high frequency inductive, high frequency capacitive, mid frequency inductive, followed by a capacitive loop, followed by an inductive loop. And this has been shown, or this has been observed for molybdenum dissolving in very high concentration of phosphoric acid. This was published by Professor Boinov et al. In 2003, and this is modeled using a film dissolution occurring through a film. Okay. So, it involves mechanistic analysis, but it also involves film, and this is the actual data, a snapshot of the actual data adapted from that publication. So, previously we showed a capacitive loop, inductive loop, another capacitive loop and inductive loop. If we remember, the charge transfer resistance would be the point here, whatever that value is, and the polarization resistance will be somewhere here. Okay. So, here the polarization resistance is more than the charge transfer resistance. Same set of loops occurring in the same sequence, but with different magnitudes, that is capacitive, inductive, capacitive and inductive, but with different magnitudes for these loops or for those inductor values and capacitor values, if we model this with electrical circuit, right. That will give rise to a pattern like this. Here the polarization resistance is smaller compared to the charge transfer resistance that occurs somewhere here, where I touch the mouse. This would be charge transfer resistance and this would be the polarization resistance. And this has been observed for nickel deposition, electrode deposition, and this is published by Professor Appelboyen in 1981. You can see that they have got data here, first capacitive loop, followed by inductive loop, followed by capacitive loop, followed by partial inductive loop. The dashed line here show that they believe that if you extend and take data at lower frequencies, it would appear like this. Most likely they have taken data at lower frequency and it was noisy or not repeatable, and therefore, they have published only data that was clean and repeatable. But definitely beyond this capacitive loop at low frequency, when you go to even further lower frequency, you can see a partial inductive loop, and that is at 1 millihertz. So, now this element has 3 inductive loops and 2 capacitive loops. That means, one high frequency capacitive loop can arise from charge transfer resistance and double layer capacitance. So, this we can explain using charge transfer resistance and double layer capacitance, and of course, this offset is for solution resistance. This is one Maxwell element, this is one Maxwell element, this is one Maxwell element, and this is one more Maxwell element. So, I have 4 Maxwell elements, that means 4 intermediates if we are going to explain using mechanistic analysis without any film, without any mass transfer, without any porous electrode structure. So, this was basically published, this was published by Professor Appelboyen in 1975, and this is for zinc deposition, and this was analyzed using mechanistic analysis. Although I have drawn them with certain magnitudes, they are of different magnitudes. You can see this first inductive loop is small, second capacitive loop is small, next inductive loop is little larger, and the last one is much larger. And of course, it was taken up to 2 millihertz and extended to real axis to indicate where the RP is likely to occur. And this of course turns in, it is not so nice as I have drawn here. Of course, what I have drawn is just artificially taken arcs and drawn them. So, it is not going to be clean in that sense. So, they have marked RT as most likely occurring here and RP as most likely occurring here. This is capacitive loop at high frequency, inductive loop at mid frequency, 2 capacitive loops at low frequencies. Again seen in ion dissolving in sulfuric acid, published in 1981 by Professor Kedem's group, and this is analyzed using mechanistic analysis. If you see the actual data, you can see the high frequency loop, a small inductive loop followed by a small capacitive loop, but before it is completed, next capacitive loop manifests here. Okay. This is a staggering of capacitive loop followed by inductive loop, followed by capacitive loop, followed by inductive loop, followed by capacitive loop again. So, this is RT, this point here is RT, 1 adsorbed intermediate, 2 adsorbed intermediate, 3 adsorbed intermediate, 4 adsorbed intermediates. This presumably will extend here and settle here at RP. Of course, if you actually model this and project this, you will not have that much confidence in the value of RP, but most likely the data at the lower frequencies were noisy or not reproducible. This was seen for iron chromium alloy dissolving in sulfuric acid and again published by Professor Kedem's group in 1986. So, this is the actual data taken up to 6 millihertz. Now, I want to show you some examples which give negative impedance meaning at low frequencies the data settles at the real axis and the value is negative. That means, RP polarization resistance is negative, and we know that it is possible because it is a negative differential impedance, it is not negative impedance per se. Okay. And often we call it as negative resistance. We have seen this for tantalum dissolving in HF, and this is one of our recent publications. At 2 different potentials in the passive region, I am sorry, it is at one potential 200 millivolt versus OCP, that is 200 millivolts anodic of open circuit potential. The experimental data shown in red color squares clearly shows that high frequency it is capacitive loop, low frequency it is a capacitive loop, but with negative polarization resistance. We analyzed it using electrical circuit. If you use electrical circuit, you can fit it well, but then getting physical meaning out of that is difficult. We have also analyzed it using mechanistic analysis, where we fitted data not just with this data, but polarization data as well as impedance data at multiple DC potentials, and if you remember right, at 2 different HF concentrations, and modeled this. The fit is not as good as what one would get from EEC, but the information we get out of this fit, even if it is a moderate quality fit, the information we get out of that is lot more. Another example to show negative differential resistance occurring with a different pattern. Okay. High frequency capacitive loop, mid frequency capacitive loop, and low frequency capacitive loop with negative resistance, seen in iron chromium alloy. So, if you see some publications in 1980s with iron dissolving in sulfuric acid, iron chromium alloys dissolving in sulfuric acid, nickel deposition, zinc electrode deposition, published by Professor Eppelbowen's group and Professor Kedem's group. They have analyzed quite a variety of patterns and were able to model this. So, a lot of these examples that I show you here, we would take from those publications. So, this is the data with first capacitive arc, second arc not going to completion, but rather halfway the third arc manifests, and at low frequency it has come up to this. Presumably if we extend it, it will settle at the real axis at close to minus 40 ohms or ohm centimeter square. Next example, which shows a capacitive loop followed by an inductive loop followed by a capacitive loop with negative differential resistance at low frequencies. Although I have drawn here with inductive loop going below, it is also possible that inductive loop may appear above this, and if you use electrical circuits, you will need an inductor to model this, or you will need to use a Maxwell element with resistance and capacitance, but allow negative values, which is basically saying you need to use an inductor in the circuit to model this. Okay. This was seen for niobium dissolving in HF. This is again the same publications where we analyzed data of niobium dissolving in HF and tantalum dissolving in HF. So, here at high frequency the red squares show the experimental data. You have a loop at mid frequencies, you have a inductive loop, high frequencies you have a capacitive loop, and low frequencies you have a capacitive loop with negative resistance. The mid frequency inductive loop is not very clear in the main picture, therefore, it was zoomed in or expanded and shown in the insert here. Model of course captures the main features, although it does not really match exactly for the data, especially at the low frequencies the quantitative match is very poor. So, another way to get the differential resistance, okay, it is not just going to go to the right side and come back and settle, not all the time. Okay. You can have a capacitive loop followed by a capacitive loop with negative resistance followed by an inductive loop. So, finally, it still settles at the negative value. Okay. This is seen for Ta dissolving in HF in the passive region. It is published in 2015. These dimensions are not the same, right. The capacitive loop is small, the negative capacitive loop is much larger, and at two different potentials the data were taken. If I remember right, the lines represent the electrical circuit modeling. In one of them, the negative capacitive loop followed by the inductive loop is clear. In the other one, it is not very visible. On the other hand, when you use electrical circuit, if I model with only one Maxwell element, even allowing for negative values, it will not model this well, it will actually come and settle like this. To capture this trend better, we need to use an inductive loop. All that it means is, in some cases you might see a data which goes like this and comes down and settle here. Another case, if you do not have good quality data at low frequencies, it is possible it goes like this, comes here, inductor's effect appears as a change in this behavior. If I have a pure capacitor, it will look like this. Because there is an inductive effect at the lower frequencies, it is getting extended. Perhaps if you are able to take data with low noise at lower frequencies, we might get a better data, but if it is noisy, then you will have to settle at some point. But the main idea is it is possible to get these type of patterns also. Not just that, extend further with another capacitive loop, still settling at negative values at the low frequency. So, for this RT is going to be somewhere here, Rp is the low frequency impedance, of course accounting for solution resistance. So, it is going to be value somewhere from this location to this location. This was seen in iron chromium alloy dissolving in sulfuric acid. As I have mentioned before, this publication has shown quite a variety of patterns published by Professor Kedam's group in 1986, a capacitive loop followed by a capacitive loop with negative resistance, polarization resistance, inductive loop followed by a capacitive loop. They have taken data up to 16 millihertz, presumably if you extend it, it will settle somewhere here. So, it actually extends like this and settles somewhere here. Okay. This is a data where you have a capacitive loop followed by another capacitive loop followed by another loop which goes like this, followed by another loop which goes like this. So, this is an inductive loop, but it is flipped. This is for example a capacitive loop, but it is flipped. Basically it means it is a capacitive loop, but associated with negative resistance This is an inductive loop associated with a negative resistance. This is a capacitive loop associated with a negative resistance. Normally, when we plot minus Z imaginary versus Z real, we expect when we go from high frequency to low frequency, a capacitive loop here means capacitance in parallel with a resistance will go like this. An inductive loop will go like this. A capacitive loop with a negative resistance will go in the opposite direction. An inductive loop with a negative resistance will go in the opposite direction. Inductive loop with a negative resistance, capacitive loop with a negative resistance. So, this basically has one capacitive loop, one inductive loop, one capacitive loop. So, 3 intermediate species. So, the high frequency capacitive loop is not very clear, but it is somewhere here, and then at little lower frequency you can call mid frequency, it is a capacitive with negative resistance, low frequency inductor with negative resistance, even lower frequency it is a capacitor with negative resistance, and this is settling at 10 millihertz. The data is taken at 10 millihertz. At lower frequencies probably it will settle somewhere here. Now, negative differential resistance does not always mean that it has to go on this second quadrant, first, second, third quadrant and fourth quadrant. Many times when we see negative differential resistance, actually we do not see negative differential resistance that often compared to a normal data at the positive regime meaning to the right side of this axis. We see it less frequently, but when we look at it, mostly we will see it is going to go like this or it is going to go like this, perhaps with one more loop here. But it is also possible that it starts here, it does not go to the second quadrant at all, it just goes via the fourth quadrant and the third quadrant and settle at negative value here. That means, this is the solution resistance at high frequencies, this is the charge transfer resistance. You have one inductive loop, second inductive loop, third inductive loops which is large such that it actually settles at a negative value here. Okay. This has been done in simulation when the date of zinc deposition, if you remember right, under galvanostatic condition was analyzed by Professor Appelboim and others, published in 1975. In simulations they have seen a high frequency loop here, low frequency inductive loop, second inductive loop and third inductive loop which will settle at the negative value. In experiments they have taken a data, it has come here, one inductive loop is seen here, it is not very clear, another inductive loop might be present or those time constants may overlap, in which case you cannot see it that clearly. At lower frequencies they have taken data up to 1 millihertz and it looks like it will go and settle at the RP value here. So, you can say experimentally they have seen data up to this, they do not have a conclusive proof that it will settle here, but most likely if you model this you can see that it would settle here. Simulation definitely they have seen, that means in mechanistic analysis it is possible for one to propose a mechanism and come up with a set of kinetic parameters such that a negative polarization resistance can come with the impedance data in the complex plane plot occurring in the first, fourth and the third quadrant only. Okay. Now, I want to describe what is called hidden negative impedance. Okay. We know what negative impedance is. If I look at a polarization curve, that is IDC versus EDC, if that has a negative slope, we know that the low frequency data in the impedance spectrum will come to negative values and will settle at negative real axis if I take data at that DC bias. Now, if I look at data here, if I take data here meaning if I take impedance data here, I would expect that the data will settle in the positive region. I do not have any reason to think that it may have a negative real value. That is, if I look at the Z real and Z imaginary, frequency Z real and Z imaginary, I do not have any reason to think that impedance data acquired at this DC potential will show a negative value for Z real. That means from the polarization data I cannot guess that this spectrum can have negative values here for Z real. However, when you actually take the data, you see that our solution is here, charge transfer resistance is there, it is anyway going to be positive, a negative capacitance loop going through the second quadrant followed by a inductive loop going through the third and fourth quadrant and settling at the positive value. So, it will settle at the positive value as indicated by the slope in the polarization curve, but it is hidden, meaning by looking at the polarization curve you cannot guess or estimate that it will have a negative value for the Z real. So, that is why it is called hidden negative impedance. Okay. It is usually seen in cases where stability problems arise. This is not one of those cases, at least not that I remember. It was published in 1985 for nickel dissolving in acidic sulfate media. I am not very sure whether it is dissolution or deposition, I will have to check. It has been analyzed using mechanistic analysis, and you can see capacitive loop going through the second, third quadrant and settling at the positive real axis. There are few other cases. This is also quite unusual. Data starts here, goes as a capacitive loop and then goes to the left, goes to the second quadrant, comes back to the first quadrant and settles somewhere here. Okay. This was published as data by Professor Pospisil and others in 2008. This data has been shown, and I think arguments were given on why it appears like this. I do not remember, to the best of my knowledge, I do not think EEC or RMA analysis was done for this. Okay. But basically this shows that this kind of data is possible. One can observe this in actual experimental cases. And finally, I want to show an example where you have high frequency data of normal capacitive data, mid frequency inductive data, and at low frequencies it behaves pretty much like an ideal capacitor. Okay. So, it just goes as a vertical line, a straight line. This was seen in niobium dissolving in concentrated NaOH, possibly at elevated temperatures, and published by Professor Boinov and others in 2003. You can see the data coming like this, settling here and going more or less like a vertical line at very positive potentials. That means its thick film must be formed on the top and it is acting like a capacitor. Okay. We will stop with this.